Welcome to my 8th ShowMe. This one is about deriving the point-slope form of a linear equation in two variables. There are 6 things to talk about here. The first is, of course, explaining what point-slope form means and where it comes from. Then I'll demonstrate how to use point-slope form of an equation to graph a line. Then we'll talk about how to use a given slope and a given point's ordered pair to generate the point-slope form. Then we'll talk about how to generate point-slope form from 2 points with no slope given, and then how to do it from a table of values. And finally, I'm going to demonstrate how to use just the information given in 2 ordered pairs representing 2 points to get the equation of a line in point-slope and slope-intercept and centered form, all in rapid-fire succession. The point-slope form of a line is simply y minus y1 equals m times the quantity x minus x1. Y and x are variables. When all the other numbers are known, these two will still be unknown. They'll still be in the formulas. However, y1 and x1 are coordinates of a point that we know on the line. So any given point whose coordinates we know could be x1, y1. And m, of course, as always, is the slope, which never changes no matter where you are on the line. To derive this, you need to think of a line as having 2 points that define it, which of course is always true. One of the points is known to us. We again call that point x1, y1. But the other point could be anywhere on the line, except of course it can't be the point that we already know. So it could be anywhere. Let's just draw it here, but the coordinates, in order to keep this as general as possible, are just x and y. Well, what's the slope of that line going to be? Well, to find the slope, we take the difference in y coordinates and divide it by the difference in x coordinates. So if we take y minus y1 and put it over x minus x1, that would be the slope of this line. Do one little piece of algebra on this and we can get right back to our formula for point-slope form. Let's say that I didn't want this to be a fraction anymore, but I still wanted it to have the same meaning. Well, we know the rules. I can do whatever I want to both sides of an equation as long as I do the same thing to each side. So let's choose to multiply each side by the same thing. I'm going to multiply each side of this equation by x minus x1. So I'm going to multiply this by x minus x1, and I'm going to multiply m by x minus x1. Well, the result of that is, on the left side, I just have m times the quantity x minus x1. On the right-hand side, I'm multiplying by this quantity over here that is exactly the same as the denominator. In other words, I'm undoing the division. These will cancel each other out. The result is just y minus y1. Well, if you turn that around, and of course the order doesn't matter as long as they stay equal, you've got the formula for the point-slope form of a line. So that formula that we just talked about a moment ago comes directly from the formula for slope. What we know about slope generates that information. Let's see how we can use the point-slope form to quickly generate a graph for a line. This is in point-slope form. This is y minus y1 equals m times the quantity x minus x1. Well, our slope then has to be 1/2. So that'll be useful. We're going to use that in the graphing by remembering that slope is always a ratio of vertical change over horizontal change, or as we like to say alliteratively, rise over run. The y, now these 2 numbers here tell us about a point that is on the line. 2 represents y1, and 3 would represent x1, but it's positive. It's supposed to be negative. How do you subtract and end up with a positive 3? That's right, you have to be subtracting a negative 3. So the x1 value we're actually dealing with here is negative 3. Now that we have a point and a slope, this graph is pretty easy to draw. First of all, graph the point. You got negative 3, 2, and then rise over run. Every time we run 2, we rise 1. So we go to the right 2 and go up 1, and this point must also be on a line. And once you have 2 points, you've got your line. So the equation looks, or the graph of the equation looks something like that. And all the information that we needed was embedded in the equation because it was in point-slope form. The information we needed to identify a point and a slope were all right in front of us from the beginning. Let's say that we're given this information. We have a line. We know that it has a slope of negative 2, and we know that it goes through the point negative 1, 5. How do we generate an equation for this line? Well, our formula is y minus y1 equals m times the quantity x minus x1. y1 would be the y value of our given point. That would be 5. So we have y minus 5. Our slope is negative 2. And negative 1 is our x1 value. Again, we're subtracting a negative. That will come out to look like addition. And there it is. This is the equation of the line we're talking about in point-slope form. And it makes sense, if they give us a point and a slope, we should be in business with point-slope form. Let's say they didn't give us the slope. Let's say they just gave us 2 points. What can we do now? Well, it's point-slope form, folks. We still need the slope. So, calculate the slope using the process previously established. The change in y values divided by the change in x values. So, for me, I always work left to right. So this is point 1, and this is point 2 for me. So my y2 is going to be negative 7. My y1 is going to be 3. My x2 is going to be 4. And my x1 is going to be 2. Negative 7 minus 3 is negative 10. 4 minus 2 is 2. Negative 10 divided by 2 is negative 5. Now we have all that we need. We actually have 2 possible correct answers to choose from. Remember that our formula, y minus y1 equals m times the quantity x minus x1. So we could have y minus 3 equals negative 5 times the quantity x minus 2. That's what we would get if we used the first point for our x1, y1. But it doesn't matter which point we use. We can use 4, negative 7 also. If we did, we would have y plus 7. Remember, subtracting a negative makes this positive. The slope is still negative 5. And then x minus 4. You graph those 2 equations, you're going to get exactly the same line. So that's how we can generate point-slope form if all they give us are the coordinates of 2 points. Let's say that we have a table of data, like the one shown here. How could we generate an equation for the line in point-slope form just using this information? The first step is to verify that this actually is a linear function, that we actually can use a line to represent the relationship between all the numbers in the x column in our domain and all the values in our y column in our range. Well, to do that, we have to understand what the fundamental property of a line is, and the most important property of a line is that the rate of change, the slope, is the same between any 2 points on the line. So if we work down this list, we should get 3 slope calculations out of 4 points. We can do one for these 2, and then these 2, and then these 2. And in each case, we must get the same number. If we do get the same slope for all 3 of these, we've got a linear function, and we can actually do the job and get an equation for this. Let's do the slope calculation. The slope calculation is change in y over change in x. 6 minus 3 for the first calculation is 3. And 0 minus negative 2 is 2. So between the first 2 points, the slope is 3/2. If the slope is 3/2 everywhere else, we're in business. For our second change, 9 minus 6, the change in y is 3. And then 2 minus 0, the change in x is 2. So far, so good. Across these first 3 points, we've definitely got a linear function. But the last test will determine the outcome for certainty. And take 12 minus 9 to get the change in y, you've got 3. And then 4 minus 2 is 2. And yes, the slope is the same throughout the table. So we do have numbers that can be modeled using a linear function. What's that linear function going to look like? Well, we're using point-slope form today. Y minus y1 equals m times the quantity x minus x1. Well, we just calculated the slope 3 times, so we're very familiar with the idea that the slope is 3/2. As far as the numbers that go in for x1 and y1, we have our pick. We can use any of these 4 ordered pairs, but the one rule is, whatever you choose for x, you must choose the corresponding y value. So let's use 2 and 9. Y minus 9 equals 3/2 times the quantity x minus 2. Now I chose to use this point. You could have used any of the other points. 0, 6 is a nice point to use because it's going to be a simpler equation than we usually see. The 0 is going to cancel some things out and make things a little bit shorter. Regardless of what you choose, you've got the right line. Any correct implementation of one of these points, any of these points, is going to give you a correct equation, and an equation that will generate a graph that's equivalent to the other 3. Now for our last demonstration. Working with just these 2 points, let's quickly generate point-slope form, slope-intercept form, and standard form for the line that goes through these 2 points. The first thing you have to do again is calculate the slope. The slope is the difference in y coordinates divided by the difference in x coordinates. I would call this point 2, its graph to the right of this, which would be called point 1. My y2 is 7, my y1 is negative 5, so I have 7 minus negative 5 on top. On the bottom I've got 4 minus negative 2. 7 minus negative 5 is 12, 4 minus negative 2 is 6, 12 divided by 6 is 2. My slope is 2. So, for point slope form, I can say y minus 7 equals 2 times the quantity x minus 4. If we do a little bit of work on that, we can quickly get to slope-intercept form. First, clear the parentheses using the distributive property. 2 times x is 2x, 2 times negative 4 is negative 8. Then add 7 to both sides, so we have y equals 2x minus 1. That's slope-intercept form. So we're 2/3 of the way there. Finally, we want to get standard form. In standard form, the x and y terms are together on one side of the equal sign. And that's not something that's happening with slope-intercept form. We need to get that 2x to the other side. Well, it's not hard to do. Subtract 2x from both sides, and you're there. If I subtract 2x on the left side, there weren't any x's to begin with, so I'm going to have negative 2x. The y will still be there, so it'll be plus y. And then, if I subtract 2x on the right side, which I have to do, because I've got to do it to both sides, all that's left is negative 1. So in that context then, a would be negative 2, b would be 1, and c would be negative 1. And we've got standard form. So that's how we quickly generate from point-slope form the other 2 forms of a line. Point-slope form is very powerful because it's a nice quick route to all the other information we might want to create. We could use slope-intercept form, especially if we want to create quick, easy graphs. And standard form is great if we're going to implement the coefficients of the line into a computer for matrix calculations. That's why you need to know all 3 of these. So let's review. Point-slope form follows this format, this formula. y and x are going to still be here when the process is completed, but we're going to calculate or discover values for x1, y1, and m. x1 and y1 form a point that is on the line, and so they're often revealed to us as an ordered pair or through a graph. And slope is our old friend. We have to calculate using rise over run. We shouldn't have any trouble with that with all the work we've done with lines. We can use this to generate a quick graph. When you know how to read this equation, you can quickly identify a point, use the slope by turning it into a ratio, rise over run. The top number in your ratio then should be a vertical change, and the bottom number should be a horizontal change. You can use either given information in the form of a slope and a point, or 2 points, to create this equation. And once you have this equation, you can use it quickly to generate the slope-intercept form in the standard form. Finally, after you've verified that the information in a table indeed does fit a linear form, by confirming that it has the same slope between every consecutive ordered pair, you can use that information then quickly to generate this form of the equation again. So this is a very powerful form for the equation of a line, and a very useful starting place whenever you have data or given information or a graph, especially when you have a graph to look at. Usually in a graph, especially a graph that's done on graph paper, it's a fairly easy matter to count up the rise and the run and calculate your slope rather quickly. All you need then is one more point, and you're in business.